Hello, and welcome back. Now, in the previous episode, I presented a rather complex way of measuring the impedance of a cable, and you had quite a lot of good feedback on that. So today, I will again look at cable impedance measurements and compare 5 different techniques and see what are the values that I get when measuring the exact same cables, and try to see which method is better, or at least what are the specific cases in which a method gives better information compared to another one. So if you're curious, then keep watching. So, first thing to look at is the RLC method. A transmission line can be modeled as an RLCG circuit, and specifically the L and C can be measured using an RLC meter. So for the capacitance, you perform an open-ended measurement, and for the inductance, a short-circuit-ended measurement. Once you have these values, the characteristic impedance of the line is the square root of the ratio of the two values, and knowing these two values, you can also determine the propagation delay of the tested line. So this is calculated from the square root of the product. And well, from this, you can get the characteristic delay, so the delay per unit of length, and of course, you can also get the propagation velocity and the velocity factor. To actually perform this measurement, I noticed that while the test leads that a generic RLC meter comes with are good enough for the capacitance measurement, when it comes to small values of inductance, these are quite inadequate. So I made a small adapter board with a BNC connector, and after calibration, I insert the test cable into this. For today's tests, I have 3 cables, which in theory at least are 50, 75, and 93 ohm cables, but we'll see based on our measurements what these really are. Well, looking at the measured values, so for our 3 cable types, I measured both the capacitance and the inductance, and then calculated the impedance using the formula discussed previously. So here, for the 50 ohm and the 93 ohm line, we are getting impedances very close to what they should be, but for the 75 ohm line, something isn't right. Now, it's true that this is a low frequency measurement. My RLC meter runs at a maximum of 100 kHz, so you can expect some deviations from what the transmission line will behave like at high frequency, but this value is off by too much. Specifically, the inductance seems to be problematic. And while analyzing this in a bit more detail, led me to observe that this cable, rather than being made from copper or aluminum, if you try it with a magnet, does contain quite a bit of iron. So we have another mystery cable on our hands. So let's see how its impedance changes with the next technique. Next method to look at is the quarter wavelength impedance transformation method. In short, based on the transmission line impedance and the resistive load value at the far end, the impedance as seen from the near end is purely resistive and can be determined using the following formula when performing the measurement at a frequency at which the line is a quarter wavelength long. This of course can be rearranged to determine the line's characteristic impedance, and in a nutshell, that is what this method is about. For this technique, I will be using the VNA connected to the test line, and at the far end, a 50 ohm termination will be added. I am plotting both impedance and reactance, so to find the quarter wavelength frequency, I'm looking for the point where the reactance goes to 0. So after moving the cursor a bit, we can find the impedance value we are looking for. Now, looking at the results, these are the 3 VNA measurements I took. So for the 50 ohm line, the 75 and the 93 ohm line, and in some cases the impedance of interest, so when the blue reactance line passes through 0, is at the top of the impedance curve, sometimes it's somewhere to the side. So that's why plotting the reactance is quite useful. Anyway, after taking out the numbers and running the calculation, we again are seeing pretty good values for the 50 ohm cable and for the 93 ohm one. But the 75 ohm cable is off again, though by a bit less than last time. Now, for some of the measurement techniques, I was also able to test them out in the circuit simulator. So when using an ideal line of 93 ohms, and then plotting the impedance at the quarter wavelength frequency, so when the phase goes through 0, if we just plot the value, and well, we apply the square root formula with the resistance value present at the end of the line, the value that is revealed is exactly the transmission line's impedance, so 93 ohms. So at least with the ideal transmission line, this method works perfectly. However, if we now move to a lossy transmission line, so this has a defined resistance, and we try out the same method, let's just change the scale a bit, well, we can see that the impedance value is a bit different. So instead of the 93 value, we are getting closer to 85. So the quarter wavelength method is pretty accurate, as long as the line's loss is negligible. Next technique to look at is the eighth wavelength measurement, measuring the impedance of a line at a frequency where it's an eighth of a wavelength long. Now, without going into too many details of the mathematics, when the line is an eighth of a wavelength long, the impedance seen is defined by this formula. It will be a complex value with both real and imaginary components. However, in two very specific cases, once when the end is short-circuited or when it's open-circuited, the formula does get simplified and results in a purely imaginary value, either positive or negative, and equal to the line's characteristic impedance. So this is how you can determine the transmission line's impedance using the eighth wavelength technique. Now, for this method, I was a bit skeptical and tested it out in the simulator first. So as before, if we start off with some ideal lines, and we plot their impedance, so the quarter wavelength frequency is the frequency at which the impedance goes to 0 for the open-ended line, so the green trace, and it goes to infinity for the short-circuited line, the blue one, and while the eighth wavelength frequency is half of this, so from 25 MHz, we go down to 12.5, and well, here we get the correct impedance value, both on one trace and on the other. Now, one interesting observation is that if you overlap the short-circuited line with the open-circuited line's measurement, well, the eighth wavelength frequency is the exact point where the two measurements overlap. So if you do perform both measurements, you don't need to calculate where the eighth wavelength frequency is, you just need to overlap the graphs and see the impedance at that point. Now, with this method again, if we also look at the lossy transmission lines, we are getting very close results, and if we zoom in a bit, we can see that we are very close to the values of the ideal lines with the lossy lines, but there is a very small deviation on the cyan trace, which is the measurement in which we're measuring the short-circuited lossy line. But anyway, in both cases, both with open-circuited and short-circuited lines, even though we're using the lossy line, we are still much more accurate than the quarter wavelength technique. So with this method, we are way closer. To test this technique out, it was again a VNA measurement, and I tried this in two ways. So first, on this upper line, I did a regular open-ended measurement, and then added in a marker at the quarter wavelength frequency, so just to see the exact frequency value, and then calculated where the eighth wavelength should be. So that's this second marker. And well, did this for all three cables. Now, the second method was the overlapping method. So here, I simply made the open and short-circuited measurements, and then overlapped the two in the VNA Saver program, and took the value from where the two graphs intersect. So with the initial method, I got the results on column F, and with the overlap method, I got the results on column G. So in both cases, we are getting more or less the same values. But I do think that if you have the possibility to perform the overlap method, this is a bit easier to go through. I mean, it's easier to find the exact frequency of interest where the impedance needs to be measured, since one of the main issues with the first method is actually finding the eighth wavelength frequency. If the cursor is a bit to the left or to the right, well, the value will be off. But regardless, we are seeing very good correlation between the measured values and what the cable should be. The next method to look at still involves measuring the impedance of a line when it's open-ended or short-ended, but this technique does not rely on a specific test frequency, but just on the multiplication and square rooting of the measured values. So it's a bit more complicated, but it should be better. Now, the general formula for the impedance, as seen from one end of the line when the other end is open or short-circuited, looks something like this. Without going into the details of what each term actually represents, the insight to highlight is that if you multiply these two quantities, most elements just reduce, and you're left with the characteristic impedance. So after square rooting, that is the only thing that remains. So while it may seem a bit more complicated, this technique, measure the complex impedance over frequency range, multiply and square root, has the advantage that it's frequency independent. In theory, it should work at any frequency, regardless of the line's length. Now, if we try this technique out in the circuit simulator with the ideal lines, and we plot out the square root of the product of impedances, well, we are getting a perfectly flat line at exactly 93. So maybe just a small deviation at the quarter wavelength frequency, but other than that, this works perfectly. Now, if we also try the same thing out with the lossy transmission lines, so this blue trace, well, we are seeing a bit of a deviation at lower frequencies. But once we move past the quarter wavelength frequency, so at 25 MHz in this case, both lines seem to give the exact same result. Now, this was of course measured with the VNA, and I saved the results as S1P files. So this is what a raw S-parameter measurement result looks like. But to get the desired values, you need to process this a bit. So I resorted to a bit of spreadsheet wizardry. So first, the S-parameter data is inserted, so for the two measurement sets. So these first need to be converted into sets of real and imaginary impedance. From this, then you perform the complex multiplication using the built-in formulas that Excel has. And then I did a square rooting of this previous value and just kept the real part. So finally, I took both the calculated values as well as the frequency and plotted them out in a graph and zoomed in to the area of interest. So this is the measurement for the 93 ohm cable. Now, we are not getting a nice straight line like we had in the simulator, but to some extent this is to be expected, since the initial S-parameter measurement accuracy is dependent on how the measured value is related to the port impedance. With S11, the best accuracy is obtained when we are close to 50 ohms. With our test lines, we're going from very, very small values to very, very large ones. So the best accuracy is obtained in the region where the line is about 1/8 of a wavelength long. And this is the region in which the curves seems to be most flat. So this is what I will use. So taking the measurement results from the three graphs and taking a point roughly in the 1/8 of wavelength frequency range, these are the values that I got for our three cables. Again, good value correlation for the 50 and for the 93 ohm ones. Now, this impedance multiplication technique, at least in my research, seems to be the best regarded one. It doesn't just cover one unique frequency like the previous ones, but rather it looks at the tested line over a wide frequency range, highlighting its change in parameters with frequency. Now, before ending our comparison, we need to, of course, measure our test lines with the TDR method. And for that, well, there are two ways of executing the measurement. So the first method is the one that I showed in a previous video. You just make an S-parameter measurement of the line and then just convert it to the time domain using some sort of program. Here you can see the line's impedance throughout its length. So while this may be overkill when you just want to see the characteristic impedance of a uniform transmission line, it's actually an invaluable technique when the line is non-uniform, like a trace on a PCB that crosses multiple layers and has all sorts of distortions. But anyway, taking some points from these measurements, averaging them out, these are the impedance values I got for this VNA TDR technique. Anyway, the other method of executing this measurement is by using a pulse generator and oscilloscope, both with 50 ohm ports. So the idea is to get the test pulse into the line and then read the reflections. But at the same time, you don't want to create reflections of your own. So for that, I found that this resistor signal combiner is the best option. To try this method out, I'm using an oscilloscope, obviously, and for the pulse generator bit, this is just a small board with a square wave generator and the resistor signal combiner. On one side, this is connected to the oscilloscope, where I have an inline 50 ohm termination, and at the other end, I placed the test cable. Then the data is read from the screen. So we are looking at the amplitude in the initial flat reflection bit. Now, with this method, to get an accurate as possible measurement, first I measured the amplitude of the generator into an open circuit and then into a 50 ohm termination. So from this, I was able to calculate the machine's impedance. Then I connected all three cables one by one and averaged out the flat bit. So rather than relying on a single point, I tried to eliminate this ripple by averaging out the value over a period of time. And then taking this measurement value and knowing the machine's impedance, I was able to calculate the transmission line impedance, so using the formula. And well, these are the three values I got for the three transmission lines. So, with all of the measurement methods tested, let's look at all of the results side by side and try to decide which is better. So, this is the overview table with all of the techniques we looked at today. The RLC method, eighth of a wavelength method, quarter wavelength method, the multiplication of the open circuit and short circuit impedance, TDR performed with the VNA, and TDR performed with the oscilloscope. So the first thing to observe is that with our good cables, so the 50 and the 93 ohm one, most methods are giving very similar results. So while we may be off by more than 10% from the nominal value, most of the VNA techniques give more or less the same value, except for the TDR, which seems to be quite off. But anyway, another important thing to observe is that if you're getting completely different values than what you're expecting, it might just be a really bad cable. Always check your technique with a good cable before ruling out some weird measurement results. But all in all, to some extent, all of the measurement methods can be relied upon. In the end, each of these methods has its use. First, you will be limited by the equipment you have, and then by the time you're willing to put in. Some methods are more laborious than others. And finally, what is it that you really need to know? Just a general impedance value, the value at a specific frequency, or if there are any issues with the cable throughout its length. Based on the need, one method or another may be preferred. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.